and Fast Forward the Green Transition, presented in 2022, in May this year, I think, has already led to some efforts to accompany it by scientific evidence of its goals. Part of it will be presented in this session. So I will chair this session. I'm a senior researcher at SINTEF Energy Research. I'm also the coordinator of the Open Entrance project, and the Open Entrance project is one of the projects cooperating with the ECEMF project about this year's ECEMP conference. We will also have two presentations from the Open Entrance project in this session. The presentations, there are 5 presentations in this session, and we have 2 hours, which means that it's around 24 minutes per presentation each presentation is expected to be around 15 minutes, and then there are around 9 extra minutes for questions and also for more practical things like exchanging presentations and so on. If you want to raise questions, I think it's the best if we go through the entire presentation first, and then we go through the questions afterwards. Then there are quite few people present now, so if you can raise your hand and show your face and just speak out, I think it's good. If you instead want to use the chat, this is also possible. Yes, so this is it. So for the presenters, I will raise my hand when you have approximately 1 minute left of your 15 minutes. So then we will start with the first presentation, developing low carbon scenarios for the European energy system, the roles of electricity and hydrogen in the open entrance storylines. And this presentation will be given by Konstantin Löffler from the Technical University in Berlin. And Konstantin, he's now a postdoctoral researcher at Technical University in Berlin, and he's also a guest researcher at DIW Berlin and the European University of Flensburg. He defended his PhD in 2021, and he has studied economics with focus on energy and resource economics and policy. And his main research areas are energy system modeling with a focus on sector coupling and long-term development of the energy system. So then I will stop sharing my slides and give the word to Konstantin.
Perfect. Yeah, thank you very much, Ingeborg. Thanks for the very nice introduction. So I will start sharing my screen. I hope that you can see it.
Yes.
And then I will begin my presentation. Thank you very much. So today I will present you some of our findings of the Horizon 2020 project Open Entrance that has been going on for over 3 years now, and it's approaching its finish in May next year. And during that, we did, from our side, so from the side of TU Berlin, we did some work on long-term pathways for the European energy system. Within this Open Entrance project, there have been 4 storylines that have been analyzed. And these 4 storylines, out of these 4, 3 of them go for a push to limit global warming to 1.5 degrees Celsius. So all of these 3 storylines, you will see them on the outskirts, essentially, of this scenario graph. And each of these different storylines tries to reach this target of 1.5 global warming essentially in a different way. So each of these storylines essentially has a whole different set of qualitative assumptions behind them, with directed transition experiencing a very strong policy push, so very strong enforcement of political targets and very strong increase in ambition on this end. The techno-friendly scenario, on the other hand, assumes a very high level of technological progress. So, for example, some new breakthrough technologies that come in there, technological advancements in general, also regarding energy efficiency. The societal commitment scenario represents a shift to more an increase in willingness of society. So things like also then sufficiency that play a role, or a general change in consumer behavior and circular economy. And then the fourth storyline, which is called gradual development, is the least ambitious of the four. Still very ambitious because it's still aiming for 2-degree Celsius target, but at the same time it has the least of all of these.
Sí, lo que pasa es que
sorry.
O sea, lo que no sé es o sea,
Thank you. And so this one has the least out of these four storylines, which means that it has a little of everything, but at the same time, usually things like, so for example, final energy demands and so on are then the highest still in this gradual development scenario, because it has the least of these ambitions in there. For these different storylines, we have used the global energy system model, or Genesis mod for short, to calculate these different storylines and these pathways for the European energy system. And in the end, Genesis mod is essentially a cost optimizing energy system model. And it's based on the open source energy modeling system Osmosis. And in general, it takes a whole amount of different inputs, so essentially assumptions on demand developments, renewable potentials, weather data, capacities in the base year, but also things, of course, very relevant like political targets, fuel prices, also technological learning curves, so technology prices also in general. And it uses all of these to then essentially match supply and demand within the model, with the demand sectors that we cover being electricity, heat in buildings and industry, and transportation for both passenger and freight transportation. On the supply side, we have a plethora of different technology options regarding both conventional power, so nuclear and fossil energy carriers, but of course also renewable energies in the form of, for example, solar, PV, wind onshore, offshore, etc. And then, of course, to match these sectoral demands, the model can then invest also into sector coupling options, either then coupling directly, for example, the electricity supply with heat, for example, via things like heat pumps, or doing indirect electrification via hydrogen. And then in the end, common model outputs include things like the primary energy demand developments, final demands on the different sectors, the energy mixes, the cost optimal technology investments, and so the capacity planning curve. We will get via the electricity mix also then the renewable generation shares and energy dispatches. And of course, then we can also compute things like CO2 reduction curves, and therefore when essentially the fossil fuels are being phased out. This entire model, together with a description, so a technical guide and some sample data set, is available publicly in a GitLab environment. And as well, we have a Zenodo group where we are trying to share as many data sets as possible so that users can actually then reproduce the results. Also, there is open platform from the Open Entrance project, which also includes a scenario explorer, where you can also essentially browse the different results and have some visualizations there as well. The outline of the model setup that we're looking at here is that we have an application that includes 30 regions for Europe. So we include the mainland EU, so we exclude Malta and Cyprus, plus the UK, Switzerland, Norway, but then also Turkey and the non-EU Balkan region, which is grouped into one node. In the end, the model timeframe covers the years 2018 to 2050, usually in 5-year steps. In the beginning, we have a 7-year step where we essentially exclude 2020 due to it being a very strong outlier and just include it in the results, usually as an exogenous data point. We use a reduced hourly time series. We're a time series reduction algorithm. So our input data is all full hourly resolution, but for computational reasons, we reduce this to a more condensed time series, usually encompassing like 72 to 120 time steps a year. As I already said, we cover the sectors electricity, buildings, industry, and transportation. And then we implement some different pathway-dependent features, like potential for demand shifting and societal commitment, political climate targets, or breakthrough of certain technologies. And I will also come to that when I show the results now. In the end, what we see in the results here is a very strong increase of the usage of electricity, which is probably not a surprise to many of you, because this is something that is being shown in pretty much all recent research. On this graph, on the top side, you see the generation of electricity in terawatt hours, and on the bottom side, you see usage of electricity. The purple bar, which is mirrored essentially on the top and the bottom, is storages. So while they are technically neither consumption nor generation, they have been shown here. So essentially get a feeling like how much of our energy or electricity supply actually then comes from these storages. In the end, of course, they don't affect the total generation numbers for electricity. What we see is that we get an extremely large push for renewables in the mix, with a heavy share of solar, wind, offshore wind, and onshore wind. And then, depending on the pathway, we do see some nuclear in there as well. There's this dark red color essentially is nuclear, although they're not really large amounts of new capacity expansions. It's rather mostly extension of lifetimes of existing new reactors. On the demand side, we get the final electricity demand, which is exogenous. So this here is electricity demand for appliances, for example, and generally like non-use in these other sectors that are covered. Whereas we also see a strong increase in usage in buildings compared to today, industry and transport. And of course, a high amount of electricity goes into electrolysis, which is this blue graph, part of the graph here. What we do see is that within each of these different storylines, hydrogen is being produced via electrolysis to a significant amount. And essentially, this also comes down to the scenario assumption that we have, that hydrogen needs to be produced domestically within Europe, within the model, within this model setting, except for in techno-friendly. In techno-friendly, we also allow for imports from outside of the EU. And you will actually see this in some of the graphs that we will be showing. When we then look at the electrification rate in the different sectors, what we can see is that in general, as expected again, same as with the total generation volumes of electricity, the electrification rate increases drastically to an average of 74% across all the different storylines and different sectors. We do see that depending on the pathway, it's different electrification rates for the different sectors. But in general, we see that 3 of these storylines are quite close together, with the major difference, an outlier being techno-friendly, where we see less electrification in industry and more electrification in transportation. This comes down to scenario assumptions in these breakthrough technologies, essentially, where hydrogen applications in industry take up more. So in the end, we have less electrification in industry due to more hydrogen there. Whereas in transportation, we allow for overhead trolley trucks. And they then lead to more electrification in transportation, where usually hydrogen is being used for example, long-distance freight transport. But so that means that in the end, if 74% is electrified, there's still 26% that need to come from different sources or from other sources, and that is then to a large share also hydrogen. If we look at hydrogen then on a regional scale, we see that since this hydrogen, as I said, needs to come completely, if not for the most part, from within Europe, essentially in the model setting, we see that the hydrogen generation is heavily concentrated in the countries of Spain and Turkey. And this is because they have excellent potentials for renewables, as well as available land, essentially, to be excellent placement options for these kind of large scale electrolysis plants. What we also see is that essentially most of this hydrogen then flows to Central Europe. We see final electricity consumption here, which is very much also centered towards more the center of Europe. And then we see that essentially these two countries are also the major exporters of this renewable hydrogen, going then again towards the center of Europe and Germany here, which are main importers of this hydrogen then. If we look at hydrogen generation, the same as we did for electricity, so top side is generation, lower side is consumption. The first thing that we notice is that this light blue bar here is electrolysis, and the dark blue bar is imports. And the first thing that we notice is only these two options on the generation side. So we do not see any hydrogen from steam methane reforming there. So no gray hydrogen. And this was also a little bit to a surprise for us, because we do allow for the generation of this gray or blue hydrogen. Both of them are available, so both with CCS and without. But the model does decide not to use it instead. Instead, sorry, someone has their microphone on. Okay. Thank you. Instead, the model just immediately goes for electrolysis in general, and therefore heavily ramps up electricity generation to be able to do so. And since the model features perfect foresight and optimizes the system more from a planner's perspective, it sees that with essentially net zero being required already in 2040, these steam methane reforming applications simply do not exist long enough to be profitable, and therefore would end up as stranded assets, and therefore the model simply does not invest into them at all. What we can also see is where the hydrogen is going. And what we see is that, except for in techno-friendly, not much is actually going in the power sector. So in techno-friendly, the largest share of hydrogen is actually going back into electrification again. In the others, it's very negligible. On the other hand, transport usually makes up a large share of hydrogen use. This is, as I said, essentially freight transport and air-based transport. And then this yellow bar here that you see below there, this is methanation. So this is then essentially the generation of synthetic natural gas, synthetic methane, which then is used mostly in industrial applications. So in our model, actually, we see that for most industrial applications, hydrogen is not being used directly, but rather indirectly through the form of synthetic natural gas. What we also see is essentially a little bit non-surprising that the more electrolysis you have, the more storages you also need, which kind of goes hand in hand with, since electrolysis comes mostly from the renewables, the model then uses hydrogen storage also as a flexibility option, and essentially uses this hydrogen use in the sectors as an additional flexibility outside of the electricity sector, essentially. So the more electrolysis, the more storages we also have for hydrogen. And what we can also see is essentially a high share of liquefaction and regasification of hydrogen, which is also a little bit surprising maybe, but is mostly due to the fact that we have strong restrictions on the flow of hydrogen through the existing natural gas pipeline network. And therefore, the model would essentially need to invest into new hydrogen pipeline capacities. And since that is also quite costly, the model then instead very much prefers also then liquefaction and regasification to transport this hydrogen throughout Europe. But this, as we've done some sensitivities on that heavily depends on essentially the assumptions that you have on the natural gas pipeline network and how much of it can be retrofitted, if at all, or if hydrogen can simply be put through these existing pipeline networks. But so this still remains essentially a big question today, is can we use this pipeline network? Because this definitely changes things in these settings going forward. So summing up, essentially, the key takeaway is that going towards net zero in 2040 or 2050 at the latest in these storylines shows a drastic increase in electrification, both for direct electrification, but also for use in electrolysis and for hydrogen generation. And what we can see, and essentially what is common across all the different storylines, is that while they are all very different in the qualitative assumptions, at the same time, they all require renewable hydrogen to work, and they all require roughly similar amounts of hydrogen to work as well. So in the end, that means that renewable hydrogen in the end will be a relevant, essentially, cornerstone as well of this energy system of the future if we aim for these very ambitious climate targets. Yeah, so that was it from my side. Thank you very much for your attention. If you have any questions, feel free to ask them in the chat or then later via email. Thank you.
Thanks a lot, Konstantin. Any questions now for Konstantin? Okay, then I think we just move on since we have used 24 minutes now, which is the available minutes per presentation. But we used some minutes in the beginning, so you are on schedule, I think, Konstantin. So thanks a lot. But
thank you.
As Konstantin said, it's also possible to contact him on email afterwards. And yeah, just to repeat one important thing you said, Konstantin, this is fully open analysis. So all the data, input data are fully open, and the model as well. So it's possible for others to start to use this and to adjust our assumptions and produce new scenarios if you want to do so. Okay. Again, thanks a lot. We will move on to the second presentation, and that is about an integrated methodology for power generation planning decision support, the case of Greece in hydrogen economy. And this will be presented by Diamantis Koutsoandreas from the DSS Lab, National Technical University of Athens. And Dr. Koutsoandreas is a postdoctoral researcher in the field of energy system modeling at the Department of Mechanical Engineering of the Aalto University. He holds a PhD in the area of decision support models and multi-criteria methods for power generation planning at the Decision Support System Laboratory School of Electrical and Computer Engineering of the National Technical University of Athens. And his research interests include also economic modeling, time series forecasting, and energy efficiency financing. So please, Diamantis, the floor is yours.
Okay, thank you, Mrs. Grabak, for the introduction. Hi, everyone. I am going to present the study entitled An Integrated Methodology for Power Generation Planning Decision Support, the case of Greece's green hydrogen economy, which has been conducted by me, Dr. Georgios Trachanas, Dr. Ioannis Papis, Dr. Alexandros Nikas, Professor Haris Doukas, and Professor John Psaras. About the structure of the presentation, I will start by presenting the background of the study and the position of Greece in this scene, which is the case study country of the analysis. Following, I will present the scope of the study and the materials and methods utilized to cover the scope. And finally, I will present the key results arising, and I will give some conclusions. Green hydrogen enjoys an unprecedented political and business momentum that is presented around the globe, which is intensified from the decreasing cost of renewable technologies. Indeed, green hydrogen could bring about significant benefits, and mainly it could assist in stabilizing variable renewable power generation through storage, as well as in decarbonizing hard-to-abate sectors where electricity is not an option or it is an inefficient option. However, there are many challenges towards diffusing green hydrogen, which are mainly related to the uncertainty about the required technologies to green hydrogen diffusion and to the shortage of the required infrastructure. Greece presents a great technical potential for variable renewable electricity and subsequently of green hydrogen. It undergoes extensive climate change aftermath, lying in the Mediterranean, and also it has been tried to disentangle its power generation from natural gas. Moreover, significant effort has been made by the Greek government towards establishing the domestic green hydrogen economy. The scope of this study is to examine the appropriate speed of green hydrogen diffusion over the 2030-2050 period in the energy sector of Greece, so as to achieve a wide range of objectives. In this effort, an innovative multi-criteria modeling approach is introduced and applied in the context of this study. Here in this slide, the flowchart of the adopted methodology is presented. At the first step, the examined scenarios are simulated with osmosis Greece, which represents the power sector of Greece with a technological detail. Here, the reference energy system adopted in this study is shown. As it can be seen at the model, all the portfolio of all the current and potential technologies that could be inserted in the system are included, while in order to model the green hydrogen production for the renewable technologies of the system, two modes of operations were set, where at the one, they channel the output directly to the grid, and at the second one, they give it for hydrogen production, so we refer explicitly in this study for green hydrogen. Moreover, due to the dependence of an energy system optimization model as osmosis is to the input parameters that are set in it, and also due to the stochastic nature of this type of parameters, some discrete scenarios are constructed about the potential evolution of technology costs, fuel prices, ETS prices, and NTS prices, as it can be seen in this figure. About the examined policies, 4 strategies for green hydrogen are examined, which are built on top of the baseline scenario over the 2030-2050 period, where each of these entails a different speed of green hydrogen diffusion and a different battery storage capacity, where the battery storage capacity at each of these scenarios is set in view of the increase of green hydrogen diffusion to not be accompanied by the increase of fossil fuels utilization. While also these scenarios are constructed with respect to the capabilities of the power sector of Greece for clean electricity production. At the second step of the analysis, the REREVITO multi-criteria decision support framework is applied, which is introduced in the context of this study and enables the identification of the energy policy that best serves the scopes of decision makers against under uncertainty conditions, and also with respect to the attitude of each decision maker against uncertainty. About the assessment criteria that are taken into account, 3 family criteria are considered, and more particularly environmental, economic, and technical criteria, where each of these family criterion is composed of one subcriterion or more subcriteria, on the basis of which they are evaluated. About the implementation steps of REREVITO, at each subcriterion of the analysis, the robustness of the examined energy policies is evaluated through applying both the maximum regret measure and the aggregate regret measure. So based on this approach, two classical multi-criteria problems are created, where at each of these multi-criteria problems, both the Vicor and TOPSIS multi-criteria methods are applied, something that leads to 4 types of results, which are classified to 3 types of decision makers. The classification of results to decision makers profiles against uncertainty is based first on the fact that TOPSIS fits better to more conservative decision makers, since apart from the distance from a positive ideal solution as Vicor does so, it also considers a distance from a negative ideal solution, while in the similar vein, the maximum regret applies better to more conservative decision makers, since it considers only the worst regret of energy policies across scenarios, in contrast to the aggregate regret that considers the holistic performance of an energy policy across scenarios. At the final step of the analysis, for the optimal energy policies identified by the Revito framework, their potential macroeconomic and societal impact on the wider economy is evaluated through the GTAP Greece model. GTAP Greece is a general equilibrium model that embodies and illustrates the interactions between the agents of the Greek and global economy and is calibrated to the GTAP database version 11. Moreover, about the financing of the examined policies, 4 scenarios are considered, where at the 3 of them, the cost is covered exclusively by the domestic economic agents, namely the government, the final consumers, or evenly by both of them, where at the last scenario, the cost is partly covered by an external to the economy grant, and more particularly from funds, from money from the Recovery and Resilience Facility Fund. So, about the results arising, first about the results of the Vicor method. Results indicate that for both risk takers and risk neutral decision makers, the optimal level of production for green hydrogen ranges in such a level from which then 15% of final electricity demand in 2050 could be delivered, while also in case that the optimal production level cannot be reached due to any type of restrictions, decision maker may opt for totally excluding green hydrogen. Results of the TOPSIS method range in the same direction for risk-neutral decision makers, while as regards the risk-averse decision makers, results indicate that this type of decision makers should adopt higher diffusion rates of green hydrogens, which could reach the level of 20% of green hydrogen-fueled electricity in 2050. While also in this case, the adoption of strategies of low diffusion rate of green hydrogen presents the same rate of desirability with the case of full exclusion of green hydrogen. About the macroeconomic analysis, when the cost of green hydrogen policies is covered exclusively by the domestic economic agents, a negative impact of low scale on GDP is observed, where this impact is less intense under the case that the cost is fully transferred and covered by final consumers. On the contrary, where a part of the cost is covered through an external to the economy grant, a significant positive impact on GDP is observed, while also this impact becomes more profound while increasing the rate of green hydrogen. And despite the fact that the amount of grant is constant between the examined scenarios. Also, the results about the impact on income range in the same direction, where when an external to the economy grant partly covers the cost, significant societal repercussions are observed. So what can be concluded from this analysis is first that the appropriate speed of green hydrogen diffusion highly depends on the attitude of decision maker against uncertainty, while risk-averse decision makers should adopt higher diffusion rates. Moreover, in most cases, an optimal production level in the level of 15% of green hydrogen fueled electricity in 2050 is observed, where this strategy would require additional 7 gigawatt and 3 gigawatt of clean energy and battery storage, respectively, as well as around 12 billion euros for its implementation, and it could lead to around 15 megatons of CO2 reductions. Moreover, and based on what I already mentioned, the implementation of green hydrogen policies should be conducted hand in hand with the increase of the system's storage capacity and clean energy capacity. And finally, the implementation of green hydrogen policies is expected to reduce a negative impact of low scale on the wider economy when the cost is solely covered by the domestic economic agents, while on the contrary, a significant expansionary effect can be observed in the case that the cost is partly covered through an external to the economy grant. So that is all by me about this study. If there are any questions, I would be glad to answer.
Thank you very much for being on time. So then there is a possibility to either speak out and raise questions or to write something in the chat. Everything crystal clear? Okay, then I just say thank you very much for your presentation, and to the audience, you as with the first speaker, you have the possibility to send questions afterwards on mail. So thanks a lot. So the third presentation will be about linking energy power system models to analyze design options for climate neutral Europe at the pan-European and regional level. And this presentation will be given by Philip Hartel at Fraunhofer Institute of Energy Economics and Energy System Technology. And he is a senior scientist and the team lead for the methods development of the energy economics and system analysis research group at Fraunhofer Institute of Energy Economics and Energy System Technology in Kassel. He's being responsible for the cross-departmental discipline of operation research. He focused on innovative mathematical modeling and optimization methods and their application in strategic and operational planning problems in increasingly integrated energy sectors and their industries. He received his PhD in electrical engineering and computer science from the University of Kassel. And as far as I remember, Philip, that was not many years ago. Maybe
2020, I think.
Yeah. And he has also been a visiting researcher at Princeton University in New Jersey in the United States and at the NTNU, the Technical University of Norway in Trondheim. So please, Philip, we are looking forward to your presentation.
All right, thank you very much for the kind introduction, and thanks for having me and then also the group or the presentation based on our work in the Open Entrance project. And yeah, I think we're the second presentation, and Konstantin has already done a pretty good job in in laying the ground, so that I can hopefully skip a few words on the background and the scenarios, because Konstantin has done a proper job there. I want to present our case study 4, which you can also find on our website. It is a case study with 2 subjects or 2 objectives, but I will go into the details later on. But the idea is mainly to bring together 2 models, so one energy system model on our side and one model at EDF, the Plan for EU model, and look into climate neutral Europe and perform sensitivity analysis based upon the pathways that we have created. And one of the sort of a tricky job in this case study is also to combine an energy sector with a more power-focused model and bringing that together. But I will go into a few details later on. I just want to say that this is joint work with Felix Frischmuth, also at IEE, who's done a lot of the modeling work, and also Sandrine Charousset and Nadia Utian at EDF. So this is a combined case study, but we'll talk a little bit about that on the next slides. Just to give you a brief overview, so I will present the introduction and motivation, objectives, and methodological approach first. We'll then briefly introduce the case study setup and show you the current and most prominent results, and then just give you a few takeaway messages towards the end, and also come back to this issue of coupling energy and power focused models, which has been also an issue in other projects that we've currently worked on. Starting off with the introduction. So when we designed the case study in the first place, there were a few things, paradigm shifts going on, of course, as we all know and have heard this morning also. It is that the low carbon energy systems will be based on cross-sectoral integration, and we've just seen again that this is a case, but really important towards the climate neutral future. We also sort of know that cost-efficient coupling of those systems will rely on the electricity sectors being integrated with the industry, building, and transport sectors. But this, on the one hand, means additional demand for renewable electricity, but it also means that we will have another source of flexibility that might be used or might be tapped into if available. And available means in time, but also in space, basically. Both is quite important, as we all know, doing energy system modeling work. The next point is, and what is maybe also a special focus of this case study, is that we wanted to look into the issue that when we model the energy system model on a sort of high level, we also want to look at it from a more regional perspective. So how do regional constraints, if we include them in our model, which typically has a country-based or one node per country resolution, how does that translate into a power sector model that has more details in the lower ground or in the lower part? And this is still subject of ongoing work. And today I'm going to talk more about the energy system model that basically runs on top of that. But just to remind you, the 2 objectives of this case study are, on the one hand, to simulate the expansion and operation of the pan-European power and energy system, while integrating relevant flexibility assets, network costs, and constraints on local and decentralized levels. This is to be done with a Plan for EU model, which is still ongoing work at the moment. And the original plan was to look into transport sector flexibility, add that sort of as a sensitivity on top of the scenario pathways that Konstantin has just presented in the earlier presentation. By now, we actually have extended that scope a little bit. So we include the transport sector flexibility, also look into cross-border integration, mainly meaning the transport, electricity transport networks, and also the hydrogen import prices as sort of a new determinant when it comes to making Europe climate neutral on the one hand, but also determining the imports dependency when it comes to fuels from outside of Europe. So this is what the case study is about, and I will talk a bit about the implications of that later on. The second but also quite important objective is to show that by using the open entrance platform, and that also includes the open entrance nomenclature that we've been working on, we can actually combine a proprietary integrated energy system modeling framework. So our Scope SD model is a proprietary model, unfortunately. We're currently trying to build up open source parallels, but this is the case as it is. So for that case study, we had to make sure that we can sort of integrate a proprietary model with an open source modeling framework, which is the Plan for EU model at EDF. And to the second objective is to show that this can also work by using the open entrance platform. So meaning using data from the platform, performing runs of our model, then giving back some data to the platform, and that can then later on be used by the Plan for EU model, and this can then be basically recast again to the open platform to have the different results and also the comparability between the different scenario runs. So this is the idea. This is, I don't want to go into the details too much. This is just a graphical overview of what we basically do. So we have the scenario framework produced by the Genesis mod on the left-hand side. So these are pathways, and we focus on the sort of 2050 scenario, which is a sort of a target scenario year, or sort of a situation but the climate neutral now. And the idea is to use the techno-friendly scenario variant, because it also features the possibility to import hydrogen, and then use that in the different modeling frameworks and perform sensitivity analysis, which this talk is about today. Just to give you a quick idea of what the models are. So the Scope SD framework that we have been developing is a static, deterministic, classical energy or integrated energy system model based on an optimization approach, meaning standard LP in the simplest form. And what we then do is cross-sectoral capacity expansion planning, so looking to all the sectors and making capacity expansion decisions and weighing them against the operational decisions and consequences in the future integrated system. This can be run as a full sort of expansion model, but it can also be run as a sort of brownfield or greenfield variant, where we sort of assume some sectors to be existing or non-existing, and then basically adapt as we go in need. The spatial focus is typically that we focus on entire Europe in a one node per country fashion. But in this case, we included for Germany and France additional regions to basically get that idea, or to see what happens in the more local domain, and also have a good interface then with the Plan for EU model that typically runs at a regional resolution, to then see the impacts on that system. But I will go into details a little bit more later on. What is also worth mentioning is that our model has a full year sort of temporal scope with an hourly resolution. So when we do the runs, we don't use any temporal reduction methods, sort of like superposition principles and representative periods or extreme periods, which is also something that we're testing and working on with other models. But in these runs that we've performed here, we basically look at the full year and hourly resolution, which has its advantages and disadvantages, but I'll come back to that in a few slides. But it was also quite good, because the Plan for E model, although it is stochastic and a little bit different in its approach, but it also looks at the full year and hourly resolution. So this was actually a good connection between the two models from a sort of modeling choice point of view. What we will focus on today is actually the first part here. So this is just a brief overview of what the scope model is. We basically have the input data. It's pretty similar actually to the overview that Konstantin gave earlier. So it goes in the same direction. The main difference is probably that we look at 1 year, then in high temporal resolution. So this model doesn't do pathways. We do have a parallel model that does that, but this approach here wasn't used for that, to be able to see all the sort of interactions between the different technology combinations that we can have. You can see in the markets section there which kind of markets we model in the scope model, where we have the heating technologies, the fuel markets, transport demands, and emission markets. And then the different technologies that sort of participate in the different markets or instruments. And you will find plenty of recent formulations down. I put them there in the comments, and you'll be able to have a look at them. So I don't want to spend too much time on that today. But we typically get out an optimized power generation mix, optimized heat generation mix, transport mix, and also a sort of consistent energy frameworks. And depending on the setup, we can also then get CO2 prices, for example, or use CO2 prices to see what sort of effect they have. One thing that is important in this context is that when we combine these sort of integrated energy system models with power sector focused models, that adds a little bit of a challenge. That is mainly due to there are two challenges. In the one direction, we have basically new fuel and opportunity decisions that we basically see in an explicit form in the integrated energy system models, that will then have an impact, or should have an impact, in the power sector focused models. So the question is, how much of that can actually be incorporated there or not? And in the other way, or the other direction, we see that we have detailed costs and restrictions on a local level and decentralized level, or maybe also on an individual unit level. For example, the standard unit commitment restrictions that we typically don't see in the convexified form that we use for the energy and power system when we use energy system models. But this is sort of a challenge that has been becoming more and more of an issue, because we're combining sort of the sort of scenario developments that we have then with power or detailed power sector models, where that needs to be translated, or at least transferred, especially when we look into these strongly decarbonized systems. Okay, now I want to go into the actual case study a little bit more. Just to give you an overview of what we cover from a geographical point of view. On the left-hand side, you see that we have sort of redefined Europe for that purpose a little bit. That was mostly due to the computational issues that we faced, because we introduced for the German market area 7 grid regions, which are based on the e-highway cluster models that have been developed in an earlier European project. And for France, we introduced 14 regions, which sort of increased the model size quite a bit. So we actually left out a few other states in this modeling approach, but then focused a lot on the regionalization of the different input data that are required. So that includes structural data, but also time series data. And as you can see, there is the electricity demand, district heating network potentials, but also the air source heat pumps, ground source heat pumps, COP factors, and all these types of things. But also the capacity expansion potentials for onshore wind or PV. I mean, they're not really PV upper bounds, but basically also the different availabilities that we see. And then also importantly, the European hydropower data sets that we have implemented across Europe, so to basically reflect that in the individual regions to a proper extent. So that is just showing you the sort of the basics, or what went into sort of the input data work. You can also see that we use the meteorological year 2012, so a historical year, no climate change impacts here, but it is the year with, according to the TYNDP, the highest Dunkelflaute index. So we actually have this period of high electricity demand, low wind, low PV, and very cold, to see sort of capacity expansions to meet that period basically in the model. So that is included. The sensitivities that we looked into are actually threefold. So we have cross-border electricity exchange capacity that we vary. We then have the share of electric vehicles or actually the charging policy, how flexible it is, and also the import price for hydrogen. And we have then created for all of these 3 different criteria. We have then introduced a low and high scenario based on various sources and also previous work, where you can see that Europe in the low version has some, or our definition of Europe, I would have to say, or add, around 120 gigawatts of net transfer capacity between the different market areas. That doesn't include the internal ones in Germany and France. And then we have another one, which is actually the large-scale RES from the E-Highway project with some 230 gigawatts, so quite a lot more, double more. Or it's double the amount of the low one. And then we have 10% electric vehicles that can charge in a flexible manner, and 90% of the individual road transport vehicles that can charge in a flexible manner. Flexible manner means then system friendly, so that the optimizer can actually make the decisions for those actors charging their way. And then what is quite important is this issue of will we have hydrogen imports in the future, and what costs may they be available? And there's been quite a lot of work going into that. Most of that has resulted in this PTX Atlas, which you can access through the link down there. But based on that work and also the CNES work that we've done with other Fraunhofer institutes, we have now 2 price paths. So one is the 45 euro, so quite a low price for hydrogen in the future, and 85 sort of as an upper price. There might be other upper prices, but this is actually with this price, we actually see the biggest changes, sorry, in the modeling framework. So I think this is quite representative of also higher prices. Now I just want to give you two insights into the modeling results. So we basically have a few results for the European energy system in total, or what we have looked at as Europe, and then also 2 deep dives into France and Germany, just to show you the individual results. When we look at the European system in total, and then again, it is, when we say Europe, we mean sort of this geographical coverage that we've put in the footnote down there. So we're missing a few of the countries that Konstantin, for example, included in his scenario pathway. We see that the biggest change actually comes from the hydrogen import price. It has the strongest effect on the capacity expansions in Europe, and the largest deviations that we can see are actually the onshore wind and solar PV buildouts. If we have a low hydrogen price, that has effects on thermal generation technologies, so it will make it more attractive to use actually thermal generation that includes CHP and non-CHP. But you can see that by far the largest impacts actually are the onshore and PV reductions that we see when we have a low hydrogen import price, because then there's almost no domestic production of hydrogen, and that shifts quite a lot. And you can also see that when we look at the energy generation that we have in the model, it reflects it a little bit more. But what you can also see here is that in those scenarios where we have a low hydrogen price, the existing capacities, and that includes to a large extent the CHP units, which are built anyway, but don't run as much in the other scenarios to produce electricity, or not that much. We'll actually see large increases in the electricity production, because the hydrogen is more competitive against building additional renewable capacity and using that to some extent. We can also see that a low cross-border integration and low hydrogen import prices drive up that hydrogen-based thermal generation even more. The transport sector flexibility also has an impact, but is among the lowest impacts that we see among those 3 different criteria. And when we look at the hydrogen import balance, we actually see this large orange part, which is the imports that we see when we have these low hydrogen prices or low hydrogen import prices. And we can see that this actually presses down the hydrogen production in the individual countries. So we've put the largest ones in here, and also the rest of Europe. We see among the different variants, we see some changing behavior. But the largest impact is actually the hydrogen import price that we see. So and that has an impact on the demand in total, but also basically the demand for renewable electricity then, and those are the highest changes that we see in the model. So this is just to give you an idea of what those different criteria can do with the energy system in the future. And when we look at the individual regions, we see that the hydrogen production facilities in Germany will be placed in the north, which is somewhat consistent with other studies that we've done. There's one issue that we have for the German case. So in this case, we have, in comparison, quite a low end-use electricity demand. So there might actually be more when it comes to higher industry demand and also household demand scenarios that we have in parallel projects. And then there's another issue with Germany. It's that we've used the 40 gigawatts of offshore wind as a lower limit for the capacity build-outs to sort of reflect the political decisions and not the more revised 70 gigawatts. The model could have decided to build more, but it didn't choose to do that. So this is one thing that is also relevant to electrolyzer deployments in Germany in the future. So, but you can see that this is somewhat correlated also to onshore wind build-outs, which is, or which you can see even stronger when we look at France, where we see that if we have a higher hydrogen import price, then there's domestic production of hydrogen, or a lot more of that. And we see that this is also then combined with, or that happens or coincides within the onshore wind build-outs, which you can see especially in the sort of these northwestern regions of France. At least this is what we get from modeling results. Now I just want to wrap up and give you some takeaway messages based upon the current status of the case study. Basically, what we've done is a sensitivity analysis based upon the techno-friendly pathway of the open entrance projects. We have looked into low and high materializations of these criteria, so the future transport flexibility, cross-border exchange, and also the hydrogen import prices. We've also demonstrated that we can use this open entrance platform to link the models and perform also the data and interfacing between the different frameworks. And when we look at the results, or the ones that we have up until now, it is that the hydrogen import price is actually responsible for the largest energy system changes that we see in the model. This is in parallel with other results that we get in parallel projects, but it also determines Europe's energy import dependency, which, of course, with the current status and as we've heard today, is actually a large factor, and this needs to be, I think, considered a lot more in the modeling runs to actually see the differences that we might get from that, because it has an impact on the demands, but also on what happens in Europe and the rest of the system when we look at these optimization models. We can see that the higher cross-border exchange capabilities make the system more efficient, as we would expect. We can also see that transport sector charging flexibility has a bit more moderate effects, I would say, but it is making the system, when we have more flexibility, this makes the system a little bit cheaper and more efficient when it comes to total use of energy. There are a few issues we need to revisit when it comes to these end-use demands and also the German offshore deployments, which is also the gap between the 370 gigawatts that we see and the 400, which is sort of envisaged for the Green Deal. And of course, we have some limitations, which is the lacking gas infrastructure representation. We only consider the fuel markets without infrastructure. We have a new model that sort of fills that gap in a linking approach, but this is has not been the focus of this work here. And the pathway dependencies, which are of course relevant, which are maybe partly alleviated through this open entrance pathway development. With that, I think I'm finished. I just want to give you one last point when it comes to coupling the integrated energy system models and the power sector focus models. it is actually that these pricing signals that we see in those integrated energy systems, this is actually quite interesting to see how that can be transported to these power sector focused models. Because if we have these hybrid demands and also the electrolyzers of how that can actually be then made visible in these power sector focused models is, I think, an important point that can be solved in different ways, better ways and less so ways. But I think that is something to maybe also take away when it comes to performing more detailed analysis, which are of course important to see how it actually pans out in the regional domain. And with that, I would like to close with 1 minute more than I was promised to have. Sorry for that.
Thank you very much, Philip. It's okay. I just let you. I just allowed you to speak because we were a bit before the schedule, so that was okay. But now it's possible to raise questions to Philip. We still have the possibility for some questions, so please.
I would have one.
Yeah.
Thank you, Philip, first of all, for the nice presentation. Very interesting to see the sensitivity to the hydrogen import prices. I was wondering whether you played around with import options for other energy carriers, methane, oil, synthetically produced, or electricity.
So what we do in the model, so we do have a sort of a parallel import option that is the power to liquid choice for the parts of the system where that is important for. That means mainly the international bunkers where we then have these additional demands. We don't have a parallel methane world with the methanation step in there. So that is actually subject of the ongoing work to include that also in the model, but that blows up a little bit the formulations even more. So we do have a methane sort of setup and a hydrogen setup, and we've used the hydrogen setup. We do have the power to liquid or sort of methane options that basically can then also be imported in a renewable manner for a price that sort of correlates with the renewable hydrogen imports. But we don't actually model the conversion from hydrogen to then methane via methanation reactors, for example. So that has not been done, at least not endogenously.
Okay. Yeah, thank you.
But I find it quite interesting because I know that you in the pipes environment now also do it. But actually this paradigm shift from having a working carbon cycle or not, that is actually quite interesting because certainly you can think about a renewable hydrogen or renewable methane world. The question is, where's that produced and where do you actually need a sort of infrastructure to facilitate that carbon cycle that might be required in the future is actually also quite interesting, and I think also subject of further analysis.
Yeah, agreed. We've been talking a lot about shipping CO2 back to where it was produced, keeping it in a cycle. Quite interesting. Definitely a lot of work to do.
Okay, but now we have to go on with the next presentation.
Thank you.
Thank you very much again, Philip. And then we will go on with the fourth presentation, Energy Imports and Infrastructure in a Climate-Neutral European Energy System. And this presentation will be given by Fabian Neumann from Technical University in Berlin. And Dr. Neumann is an energy system modeler at the Department of Digital Transformation in Energy Systems at TU Berlin. He researches cost-optimal pathways for the energy system with a particular focus on revealing the trade-offs between energy resources and network expansion, flexibility, and public acceptance of new infrastructures. He is also a strong supporter of openness and transparency in research data and software. And he is one of the co-developers of the widely used open source modeling framework, PIPESA, which stands for Python in Power System Analysis. Before joining Technical University of Berlin in 2021, he defended his PhD in computer science from the Karlsruhe Institute of Technology. So then, Fabian, please, we are looking forward to your presentation.
Great. Thank you very much for the kind introduction. At last year's ECEMP, when it was still called EMPE, we presented a study based on the same model I'm going to show results of today. But we looked at only self-sufficient energy scenarios, so meaning that Europe in a net zero world, European energy system would fully supply its energy demands inside Europe. Now, we've had previous presentations in this session looking at imports in the technology-friendly scenario, allowing imports from outside the EU, and similarly, we thought this would be a very nice case study to look at in today. So I kept the introduction short because you all know it, and we've talked plenty about this before. But the premise is a little bit that building the energy infrastructure within Europe to achieve a net zero emission system does not always meet the high levels of acceptance in Europe that would be needed to allow for a swift transition. Think about public acceptance problems with onshore wind developments and power grid transmission expansion. Whereas on the other hand, other parts of the world have very cheap and abundant renewable resources to offer to global markets, more than they would need themselves, and they could become key energy partners for making net zero happen in Europe. Not only in Europe, but also worldwide. So obviously, there are more nuances than just cost when we discuss how much imports do we want in Europe when we go to a net zero world. But in this study, we looked at trade-offs between a fully self-sufficient net zero system in Europe and more import-dependent scenarios where much more of the renewable energy is imported from outside Europe. So we will touch on questions like what cost reductions could we possibly achieve through energy imports? How sensitive is it to the amounts of imports that are imported? From where do we import these resources, and to where do we import it when we think about the landing points inside Europe? And linked to that question is also, how does our strategy on imports depend on the infrastructure needs inside Europe? So think about what grids, energy grids, electricity, hydrogen, gas will need, and how much it depends on what choices we make on the energy imports. So we coupled a global supply chain model from Johannes Hamm with our open all sector energy model, perhaps the EORSEC, which I'll briefly explain, but in principle, it's very similar to what Konstantin and Philip presented before, that we have a model where all the demands are represented. So not only the electricity demands, but all the different heating demands, transport, land transport, aviation, and shipping, as well as industry demands. And in industry demands, we're also looking at industry feedstocks, ammonia, and oil for plastics production. So we'll have different supply options to meet these demands in the heating sector: resistive heaters, heat pumps, gas boilers, and CHP plants that are sourcing from wind and solar PV, hydroelectricity, some biomass resources, some fossil gas under certain circumstances, as well as from the atmosphere for the heat pumps. And then the focus is really to look at how do we balance the supply with demand through grids and storage, and how does the energy conversion between the different energy carriers work, and also how does the carbon cycle work. And what we added now is the import options. So that's an additional source from where primary energy can enter the European energy system. So if we want to look at infrastructure in infrastructure effects of imports into Europe, we need spatial resolution inside the European network. So here's on the right-hand side a plot of the ENSO-E transparency map. Obviously, we can't solve it at that high resolution, but we'll go beyond the 1 node per country resolution because we're interested in a more granular networkology, how the network topology of different grids will play out inside Europe, depending on import choices. So the energy networks are obviously very important to capture the diversity in renewable potentials across different regions within Germany, within Spain, etc., and also for the infrastructure. The other dimension that is very important, which we also talked about in the previous talks, is the temporal variability, which needs to be captured, particularly in the heating sector, as we're all anticipating for the current winter. This is very challenging to renewable energy system models because there are difficult periods in the winter with very low wind solar feed-in, high space heating demand, and also additionally low air temperatures, which are bad for air source heat pump performance. So on the left-hand side, to give you a feeling about the total final energy and non-energy demand that we consider in the system, it's about 10,500 terawatt hours, which is a good number to keep in mind when we are talking about the import volumes in the upcoming scenarios. One thing that we recently added to the model, because infrastructure was a topic under investigation, we added the gas transmission network based on the Cygrid gas datasets from DLR, which was recently published. It's an open dataset of the European network. And we supplemented it with some additional LNG terminals and pipeline entry points from the Global Energy Monitor wiki, which we then could use as import to find out where possible entry points for energy imports into Europe could be. So here's 2 or 3 slides about the model of the global green energy supply chains. So how we form the import prices that we feed to the European model. We considered 16 exporting regions. This is not a complete global view, but it's including some of the countries that have been hotly discussed in the for the energy imports. We consider as import carriers hydrogen, methane, ammonia, fish trough fuels, and also electricity, reviving some of the desert tech vibes from 10 or 15 years ago. For some of the hydrogen and methane, we consider both pipeline and shipping supply routes. So some of the Northern African countries, for example, they also have the option to supply these via pipelines. So that's about the export regions. For the import, we also consider different import corridors. So we look at where the landing points at the European coasts could be, and then the distances also vary, and that also determines the import costs at that node. So the renewable electricity, we consider what land could be eligible, and we also reserve some of the cheapest electricity in the exporting countries for the domestic demand, which is not much in most countries compared to the compared to the total potentials. But based on this electricity, we then put it into a supply chain model for the different components. So here's an example for a Fischer-Tropsch energy supply chain, taking the electricity and then sourcing hydrogen, electricity, and CO2 to produce Fischer-Tropsch fuels and then ship them, whether then enter the PISA-ERSEC model. So what's going into the model is a volume of imports that are possible at a certain price, so supply curves for levelized cost of energy, not only for Fischer-Tropsch, but also for the other energy carriers. So here's how it. So here's a more focused view on how do the import options enter the European model. So this will give you a feeling for the spatial resolution that was applied in the study. In orange, you will see the current LNG terminal capacities. So these are entry points for shipping hydrogen and methane. In purple, you'll see the pipeline entry points into Europe, for which we allow pipeline hydrogen and methane imports. Two further carriers that are not spatially resolved are ammonia and Fischer-Tropsch fuels. And in the top bar, you can see sort of the cost ranges, the cheapest cost ranges that we assume. So if I put it into perspective to what Philip's numbers were, so the cheapest hydrogen import options via pipeline are around 55 euros per megawatt hour, compared to the 45 euros per megawatt hour that Philip had. And then it goes up to 80, 90 with liquid hydrogen, and also depending on the exporting country. The electricity is added as individual nodes and time series, as well as the HVDC links, the solar and wind investments, the battery storage and hydrogen storage in these countries is endogenously optimized in these models. So it's not a fixed supply curve that is added there, but it's co-optimizing the infrastructure in combination with the European system. So here's a summary before I show you some results. We couple all the energy sectors: power, heat, transport, industry, feedstocks, agriculture, and international aviation and shipping. Reduce net CO2 emissions to 0. Look at 128 region aggregation and 3 hourly time steps. And then we have power, gas, and hydrogen networks developed, included, where the power grid capacity is allowed to expand to about double what it is today. We choose technology assumptions for 2030, mostly coming from the Danish Energy Agency, quite strict on the CO2 sequestration potentials of 200 megatons. And then we vary the allowed import volumes and import carriers. So, we step right into it. So here, I'll give you some orientation. On the left-hand side, first of all, this is bar plots of the total system cost. On the left-hand side, you see a scenario where we don't allow any imports. On the right-hand side, you see a scenario where we allow the model to choose which energy carriers to include and how much cheaper this option is. So in this case, it's up to 7% cheaper, where then 30% of the total system cost would be spent on energy imports, whereas 70% would be spent on intra-European infrastructure. All the solutions in the middle, they make some assumptions about, they implement some restrictions about what energy carriers can be implemented. So if I allow only ammonia or only methane, that will only give me a very limited benefit in our initial scenarios, whereas hydrogen and electricity can give already quite a big share of the maximum benefit we saw. So half of the benefit from exclusive hydrogen imports and 5% from exclusive electricity imports. So I should say that all the results I'm presenting today are preliminary and primarily to start a discussion with you about what you think of these results. We'll definitely do a revision of these in the future. But nonetheless, I think it's very interesting to get a first feel of what the sensitivities here are. So here's another plot. People who have seen previous presentations of our group will know this type of plot. But here we look at the system cost and while varying the allowed import volume. So from 0 terawatt, and so no imports to 10,000 terawatt hours, which is almost 90% of the final energy demand. So we start out with the 700 tons, and we see that already half of this benefit, this 7% benefit, can be achieved with imports below 1,000 euros. And you can also see that the solution space is very flat in a very wide range of import volumes. So from 0 to 8,000 terawatt hours, we are still below the 700 billion euros per year. So this will tell you maybe it's not cost that driving our import strategy, but other considerations. So I'll come back to that in the conclusions. I wanted to give you also a more geographical view of where the imports occur. But first, you'll need to have a reference where there are no imports. So here you see in the blue colors the Power-to-X investments. So where there's a lot of electrolysis, Fischer-Tropsch fuels, methanation. So you see it's focusing mostly on northwestern and southern Europe. And then the grid expansion that is shown in red that focuses mostly in the northwest of Europe. So how does it change if we now allow imports? So the next picture I'm going to show will allow the import options. So what happens to the grid? Well, the grid expansion, there's still some grid expansion in northwestern Europe to support the remaining PTX production in the British Isles and Denmark. But now, as we see also electricity imports from North Africa, Ukraine, and Turkey, there's some diversion of the grid expansion to southern and eastern Europe. And there's, because the electricity from the imported electricity needs to be integrated, and our restriction of a doubling of power grid capacity also leads to a more even distribution of the imports of electricity. Now, in purple, you see from where the hydrogen would be imported. So there's a certain share. So it's about 40% of the imports are from hydrogen. They occur in Italy and southern Spain. And then there's some fragmented methane imports in northern Spain, southern France, and the UK. Interestingly, both wind and solar are built for the electricity imports. Our current working theory is that it's for seasonal balancing of wind and solar. So this is my last slide for the content. Here we looked at how do the flows in the hydrogen network that is being developed change. So it changes from distributing the hydrogen production in the North Sea region, from incorporating the imports from North Africa. And if we look at the energy that is transported with and without imports, then the hydrogen network is used much more to distribute than the hydrogen imports from Spain and Italy to Central Europe, where most of the demands are. So some preliminary conclusions and also some discussion points we can touch on in the questions. We found a maximum cost benefit of 7% of the imports. That also means that we can implement self-sufficient Europe if it's worth 7% to us. What we should keep in mind is that the European energy infrastructure heavily depends on the strategy taken on imports. And given the flat solution space, other factors than pure costs might rather drive the import strategy. So geopolitical considerations, building a more simple or easy to implement systems with fewer connections across the sectors, reusing existing infrastructure, for example, gas pipelines from Northern Africa, resilience of supply chains, and also technology risks where certain technologies may not become available in time. Final statement is that all of these results strongly depend on the assumptions and modeling approach taken. So more work on this will come soon on doing import cost sensitivities like Philip has done, losses inside the European energy networks, industry relocation, and material imports are some of our current discussion points on this work. And thank you very much.
Thanks a lot, Fabian. Questions for Fabian?
I would have a question, but I can also wait for some other.
Yeah, please speak out, Philip.
Okay, very, very interesting, connecting everything. I'm not sure whether I've sort of grasped everything properly yet, but it's highly relevant, I think. And I just have two questions. So one would be when you show the potentials in the different like abroad countries, basically. Have you factored in the way you were showing the sort of these exclusion like layer files earlier of Chile, for example? I can't really recall the country.
I think it was Argentina. Yeah.
Oh, Argentina. Have you looked into water availability or factored that in as a factor? Because that might limit sort of the production closer to shore or something, which is something that we have sort of experienced in this Power to X Atlas. And the other question, which is related, is rather common, I guess, is have you factored in the sort of the transitions in those exporting countries? Because I mean, it has sort of a neo-colonialistic flavor to some extent. And the question that we are concerned with right now is what happens in those countries and how much of that would actually be available for export and how much of that would be required themselves or in those countries themselves. So I think those two comments or questions.
Okay, yeah, thank you. For the water availability, I believe it's not taken into consideration, but my colleague Johannes Hamp is in the chat, and if I'm wrong, then he will shout in the chat. So about the argument, well, what about the transitions in the exporting countries? We make some reservations for the domestic demand. I think that includes should include the all energy sector, but again, Johannes will correct me in the chat if that's not correct. So yeah, I think it's a sensitive discussion. I think there's in many of the exporting countries there's more than enough potentials. That is also that the levelized cost of electricity don't rise as quickly. So that's still a cheap export options, and I mean they could also become the exporting countries could also thrive economically from doing the exports, provided that they can also realize their own energy transition.
Fully agree. I just wanted to ask whether that's an issue that you've considered yet.
Okay, it's only 25 minutes left, so that is what we need for the last presentation. So again, thank you a lot, Fabian. And then we go on, as I said, with the last presentation, which is 24/7, a new paradigm for power procurement. And this presentation will be given by Igor Repin, also from Technical University in Berlin. And he holds a PhD degree in energy economics. He is a postdoctoral researcher at the same department as Fabian, digital transformation in energy systems at TU Berlin. And generally, he does the research in the field of energy economics and energy system modeling. So he will share in his talk the first findings from a research project on the system level impacts of 24/7 carbon-free energy procurement. So please, Igor, the last presentation for today.
Yes, yeah, I unmute myself. Thank you very much for this introduction. Very nice to be first time at ECEMP, and very nice to meet with many of you here. So yes, I'm the colleague of Fabian, and I think accidentally I'm the third person from TU Berlin in this session. The aim of my today's talk is to share with you some of the results our team has from the first 6 months work on the project, which is dedicated to 24/7 carbon-free energy procurement topic. This is the joint work with Tom Brown, and the study which we are undertaking itself is funded by Google. So to start with, I will give just a quick introduction. What is 24/7 carbon-free energy procurement and why we are interested to model it? The background for this is that many companies from corporate sector or from industry sector They are buying renewable energy to the extent sometimes above and beyond what local energy markets provide. They do it to provide or to highlight own renewable statement or to contribute to the energy transition. These purchases can be done in two ways. They can either procure renewable certificates of origin. This is basically like PPA the bundle decoupled from the generation, or by purchasing the energy directly via form of power purchase agreements, PPAs. The PPAs for renewable energy are typically designed to match generation consumption on average over a large period of time, like a year. So what this picture on the slide shows, this is a snapshot from the 800. This is the organization which joins together more than 370 companies that have joined together in an effort to buy enough renewable energy so as to cover their consumption on average over a year. And these voluntary commitments, like 800, they do many goods for the system. So one way how they contribute to the system is they accelerate the deployment of renewable capacity. And this ways, such voluntary commitments drives the decarbonization. And on the other hand, the early players in the field of carbon-free energy procurement, they pave the way for others to follow by establishing some standard schemes for PPAs, as well as to building up the investor confidence in renewable energy. There are, however, several problems connected to 100% renewable matching, which is incorporated into the design of the schemes. So one of the major problems with 100% renewable matching is illustrated on this chart, which shows some illustrative example of carbon-free energy supply, which can be a combination of solar and wind, as well as the electricity demand of electricity buyer, which is here just flat profile of data center, but it could be any profile. So one of the obvious things, which is a problem with 100% renewable matching, is a mismatch between generation and consumption. So there obviously can be hours when the renewable portfolio designed for 100% renewable matching will oversupply then the demand on hourly basis, and there will be hours when there will be not enough solar or wind generation to cover the demand. And in these hours, the electricity buyer would need to go to the market, procure electricity, which is not necessarily 100% clean, and thus the consumption portfolio will have some carbon content. This is one of the major problems connected to 100% renewable matching, but there are many more. So some of the most discussed ones are the displaced location. This is the case when consumption is located in one country, like Germany, but the PPA is signed with generator located in another country, like Spain, and in case there is a congestion, there is a problem of carbon accounting. There are more problems like risk exposure, because the electricity buyers would need to go to the market and buy at market prices, which are volatile. And the last but not least, a very important problem with the scheme is that this scheme lacks for providing incentives for some of the advanced technologies, which is not now in the market, but they are needed on the market later. The reason for this is that in order to assign the PPA with some generators to achieve 100% renewable matching, the electricity buyer would seek to decrease the PPA cost, and the cheapest technologies which can provide the least cost solution to generate enough electricity on volumetric basis are wind and solar, and not technologies like closed loop geothermal or advanced nuclear or Allen cycle CCS, which are needed for deep decarbonization of energy systems, but are costlier than wind and solar now. So for this reason, there is a growing interest from leaders in voluntary clean electricity procurement to cover their consumption with clean energy supply on truly 24/7 basis. So 24/7 basis mean that actually every kilowatt hour of electricity consumption is met with carbon-free electricity sources every single hour on every single day. And so basically the ideas behind this 24/7 CFE procurement is to address the series of problems which exist with 100% renewable matching. So to insist that demand is matched on an hourly basis, to insist that contracted power is additional, to insist that power comes from the same bidding zone, and that power is carbon-free rather than renewable. And 24/7 is not absolutely new thing. At this point, there is this 24/7 Energy Compact. This is an initiative launched by the United Nations last year, which already has 80 companies, organizations, institutions, which together aim to reach 24/7 goal. Okay, so I joined to study design, where I have just one slide with the name to showcase what we have done in this 6 months work modeling 24/7. So we want to investigate both the means, basically portfolio combinations, and cost for 24/7 procurement for companies located in European countries, and as well as the system impacts the 24/7 procurement can have for the rest of the energy system. And for this purpose, we do the following. We take a standard state-of-the-art electricity system model, which is open source, very well documented to a large extent by Fabian, who talked before me. And by modeling European energy system, we specify a fraction of corporate and industry load. So basically, we narrow down some load located in some portions of the network that commit to voluntary clean energy procurement. So procurement itself is modeled by a set of equations. For example, the 100% renewable matching constraint would enforce some share of a load to procure just enough electricity so as that 100% consumption can be matched on an annual basis, as well as the 24/7 CFE constraint would require that this load that commits to this policy needs to procure portfolio in such a way that the generation from this portfolio, as well as the grid imports, can match hourly demand with clean energy to some extent. And this extent we will be calling CFE score. And so basically, if CFE score is 100%, this means that every hour, every day, the generation is met with carbon-free energy. And if CFE score is lower than that, that means the target is achieved to some extent. And in our study, we explored different countries. Naturally, the countries in the European energy network differ by renewable potentials, by local resources, legacy fleet of power plants, national policies, and many else. And depending on where you are in the European energy network, it can be more difficult or less difficult to achieve 100% CFE or some other target CFE procurement. As well as we explore different years, different shares of demand, different load profiles, and so on. And all of this to generalize and understand the impacts of 24/7 procurement. About results and takeaways. So from our studies that we have done in this first 6 months, we have basically the 5 main takeaways that we want to share with society and with you. And I thought that makes a lot of sense if I just put all of the takeaways to the very start of my results, and I will go through them and then back up the statements with some of the plots afterwards. So basically, if you wish to have one takeaway with you from my talk today, you can choose any of these 5. So takeaway 1 from our modeling is that reaching carbon-free energy for 80 or 90% of the time has comparable cost and system impact to annually matching 100% renewable energy. So basically, for these targets, the commercial industry participants who join the voluntary procurement can buy somewhat different portfolio than for 100% RESF target. But the cost for this portfolio and the system impacts for this portfolio will be comparable. Then reaching 100% CFE is possible, but it's very, very costly. If you have in your portfolio just renewable energy, solar and wind, and storage technology. The reason for this is that in order to match clean electricity from wind and solar with demand on an hourly basis, you need a very, very large portfolio, and then you need battery storage to match the two. We find that typically the cost increase very rapidly above target of 95%. Then in case CNI participants who commit to voluntary procurement have an access to and add in their portfolio some advanced technologies like long duration energy storage or advanced nuclear or natural gas alarm cycle with 100% CCS, the cost premium can reduce drastically. First takeaway is that 24 CFE procurement leads to lower emissions for both the buyer and the system, as well as the system-friendly CFE. So basically, the portfolio that is designed to follow the load impacts the system in a way that the flexibility needs are greatly reduced. And the final takeaway is that CFE procurement creates an early market for some advanced technologies that system needs later for deep decarbonization by stimulating innovation and learning from which the whole system benefits. Okay, the 5 takeaways from our study. And I back up this up with some of the plots for nearly randomly selected scenarios. This scenario is for Ireland, year 2025, 10% participation, meaning that 10% of commercial industry load located in Ireland, so this is nearly 200 megawatt of load, follows clean energy procurement. And this plot shows the fraction of hourly demand met with carbon-free electricity. So the matching with carbon-free of demand and carbon-free electricity can be done by 2 ways. By either procuring some resources, this is mapped with pinkish PPA chart, and then by having some grid imports. So the reference case, which is displayed, which yields 61%, this is a case when there is no procurement policy, when this 200 megawatt of load simply buys energy from the grid, and by doing so, they achieve already some percent of demand, which is met with CFE, which is 61% in this case. 100% annual renewable matching yields already 85% fraction. And naturally, once we go more tight with CFE score, which is depicted here from 80% to 100%, at certain point here, it's above 85%, the hourly matching yields higher share of demand met with CFE. And another finding is that for 100% CFE, it's expected to have that the CNI participants rely more on resources procured themselves rather than the grid, because grid is never 100% clean. Then the second metric which we analyze in the study is the average emission rate of CNI consumption. So this is ton of emissions associated with participants' demand over a megawatt hour of consumption. So already in 25, Ireland has a moderately clean electricity system at around 140 kilogram per megawatt hour. And 100% renewable matching, which is the best case of the annual matching policy, yields already great decrease of emission rate up to 50 kilogram per megawatt hour. And this is way above, or somewhat above, what lower CFE scores like 80 can provide. With tightening the CFE score, the emission rate drops up until null. It's expected to have, because with CFE 100, basically every hour is matched with carbon-free electricity. So the question is at which cost this is possible, and this is depicted on the next plot. And this plot depicts basically portfolios that CNI participants sign contract with, and in the form of costs paid for this portfolio. So the bars consist from the cost, which is basically capex and opex of generation from these technologies, divided by megawatt of consumption of CNI participants. And in this plot, there are 3 technologies: solar, wind, and battery. And the cost of grid imports are marked by light green, and the cost of selling the excess energy from the portfolio back to the grid is marked with the dark green. So as expected, 100% RES procures just wind and solar. And in some hours when there is not enough wind and solar generation to cover the demand, 100% RES would also buy some energy from the grid. The highest CFE targets includes battery storage because you need it to match on hourly basis. And what we observe here, and what also we observe for all of the countries, is the fact that above 95% CFE target, the cost premium rises rapidly. So here the 98% CFE cost premium is just about half above the 100% RES, but the last 2% of CFE target would require as much as double the cost to achieve this target. And in case long duration energy storage is available in the market and C&I participants can contract it and add it to their own portfolio, the cost can be greatly decreased. So on previous plot, the PPA cost for the 100% CFE score is at around 240 euro per megawatt hour. And in case LDS technology is available, the net cost is at more than double less, so it's around 100 euro per megawatt hour. And of course, these results are greatly depend on the cost assumptions. Here we assume 2.5 euro per kilowatt hour energy hydrogen storage, as well as they depend on the cleanness of the system and many other parameters. So the absolute value to which extent LDS can decrease the cost vary, but we observe this dynamics in every country, in every scenario. And finally, in case the advanced clean technology is available in the market, the costs can drop even further. In this case, in Ireland, the portfolio includes natural gas Salem cycle generator, and the cost for achieving 100% target for annual matching decrease to at around just above 80 euro per megawatt hour. This yields roughly 20% cost premium on top of 100% renewable matching, but in our scenario space, we see some cases when the grid is relatively clean and when the excess energy can be sold to the network, then the cost premium can nearly disappear. Okay. The final slide from my result is the carbon emissions in the regional grid. So basically, in our report, we investigate several metrics how the 24/7 procurement can impact the rest of the system. And carbon emissions in the regional grid is one of them. So what you can see here is emissions in Ireland, and is a reference case when there is no procurement. So basically, the participants just buy energy from the grid. The power sector system emissions at around 3.5 million tons CO2. So just for comparison, this value actually for Ireland in 2020 was 8.4 million tons. So this is a very plausible result. And then 100% renewable matching can deliver a greater level CO2 emissions reduction than low targets from CFE matching. In this case, up to 0.6 million tons CO2 per year. But naturally, the high CFE scores up until 100% hourly matching yield a greater system reduction cost. This is something natural to expect, but this result should be seen in light of a previous result of cost of achieving this. So there are cases when some combination of technologies available, then C&I participants following 24/7 procurement can achieve zero emission rate for own portfolio and can greatly impact the system by lowering its emissions, as well as by reducing the system flexibility needs at almost no cost premium or at a very minor cost premium. All right, this is the last slide for me. The study which highlights this first 6 months of modeling we have done this project will be released next week. So if it's something interesting for you, you can send me an email and I will forward it to you. as well as all input data in the code, as well as instructions needed to repeat the results we have here and play with it yourself are already on GitHub, and under the MIT license, you can check it out in pipesa/247CFE. Thank you.
Thank you very much, Igor. There is a few minutes left. It's a question for you in the chat, I think. Is the cost premium marginal cost or research rent?
So let's come back to the slide. So we speak about this slide. So this CI cost is basically the capital cost for this technology, operational cost for this technology, divided by the consumption. So this is like average cost. And the cost premium then is the difference in average cost of having this portfolio. I think this is much represented to the cost you would expect to sign PPA on competitive market. So I would not attribute it as marginal cost, but rather the average cost.
Okay.
I hope this answers this question.
Yeah. There's also a question, more general question, whether this recording of the session will be shared with the participants. And the answer to that is that yes, the recording will be published on the website of the conference at the end of the conference. Any more questions to Igor or to any of the other presenters? Okay, it's then only, as I said, 2 minutes left. So thank you so much, Igor, and to all the 5 presenters. And thank you to the audience. We close this session. And if there are any more questions, please then send them to the presenters afterwards. And as I said, you can also then look at this session again after the end of the conference. Thank you all.
Thank you.
Thank you very much.